In this video, we will learn about integration by parts. The concept of integration by parts is an integration technique that is essentially the reverse of the product rule for derivatives. Now, when we first talked about integration rules, remember that in general, there is no rule for the general integral of a product. If we try to integrate f of x times g of x, there's not a rule that will always work to integrate a product. We can have some fairly simple looking products that don't have an antiderivative, which we can write in terms of elementary functions. So integration by parts is not a product rule for integrals, but it does come from the reverse of the product rule for derivatives. Here's the formula for integration by parts. We start with an integral which is of the form some function u times dv. This will be generally in terms of x. And this integral can be written as uv minus the integral of v du. Now, this might look a little bit strange at first, but as we practice with it, it will look more familiar. Let's start by going over a quick little verification of this formula. This isn't a formal proof, but it will give us an intuitive idea of why this formula is correct. We can abbreviate integration by parts as IBP. So let's consider two functions of x. Let's consider u and v as functions of x. And I want to consider the product uv. Now imagine taking the derivative of this product, which we can do using the product rule for derivatives. If we take the derivative of uv, we would first find the derivative of the first function, du dx, times the second, plus the first function u times the derivative of the second. That is the product rule for derivatives. Now, imagine if we were to integrate both sides of this expression. We have a function on either side which are equal, but imagine integrating with respect to x on both sides. Well, on the one side, we are integrating a derivative. Integrals and derivatives are opposites of each other, so the integral undoes the derivative, and we are simply left with uv. On the other side of the equal sign, we have the integral of a sum, two functions added together. We can split that up into separate integrals. We can write the first integral as the integral of v times du dx with respect to x. Now, notice I actually switched the order of the du dx and the v, but we can switch the order of these and it's still the same integral. The second integral is the integral of u dv dx, again integrating with respect to x. All right, here's a little bit of an informality with this, but we can essentially treat this derivative notation du over dx as a fraction, and we can imagine canceling the dx's, the same with the second integral. And when we do that, we have the integral of v du plus the integral of u dv. This all equals u times v. Now, if we subtract the integral of v du from both sides, then we'll obtain the formula for integration by parts. The integral of u dv, that's coming from this right here, equals uv minus the integral of v du. So we can see that undoing the product rule for derivatives gives us this formula for integration by parts. This is a very important integration technique, and we want to have this formula memorized. Let me show you a little jingle that helps us to memorize this. We can memorize this formula using this silly little phrase, ultraviolet voodoo. All right, this will probably be forever stuck in your memory if you say it several times. Ultraviolet voodoo, ultraviolet voodoo. And what on earth does it mean? Well, U, ultra, that's the U for the UV, and then V, violet, that's V, so ultraviolet UV. And then we have to remember minus the integral, and then V, that's the V inside the integral, du, du. So there we have it, ultraviolet voodoo. If you ever find yourself forgetting the formula for integration by parts, just try to remember ultraviolet voodoo, and hopefully that helps you out. All right, let's talk about the procedure for integration by parts. Then we'll work through a couple of initial examples. How do I use this technique to evaluate an integral? Well, we first take our integral and we split the integrand into two factors. One of them we label as u, and the other we label as v, dv. And just as a suggestion here, u should be simpler after we take a derivative, after differentiating. And dv should be easy to integrate. Once we've found u and dv, we're going to take a derivative to find u, we're going to integrate to find v, then we substitute into the integration by parts formula and solve the final integral to get to the end of the answer. Let's see this in action with example 1. For example 1, we have the integral of x times e to the x. Now, I want to view this integral in the form the integral of u dv. So part of this integral I'm going to call u, and the rest of the integral will be dv. Now, we'll talk later about strategies for choosing u, but for this one, the right choice is u equals x. So I pick part of the integral, split it into two factors, label one of the factors u, we're picking u to be x, and everything that is left automatically is dv. So I've picked u to be x. Everything left over is dv by default. Once I've chosen u, automatically everything left has to be dv. Notice that dx is always part of dv. So I have u, now I will write dv. dv equals e to the x dx. It's everything left, including the dx. dv always includes a dx. All right, that's the first step for integration by parts. For the second step, I want to find du by taking the derivative of the function u, and I find v by integrating dv. So there's a really interesting symmetry that happens here. We take a derivative of u, and we take an integral of dv. The derivative of u is just 1, so du dx simply equals 1. But we want to write dx in terms of du, so I'm going to multiply both sides by dx, and I will obtain du equals dx. We'll often skip this intermediate step, and we'll go straight to this step where we have du written in terms of dx. So du equals dx. Now to find v, we integrate dv. Well, dv is e to the x dx, so we integrate e to the x dx. The integral of e to the x is simply e to the x. So this is the function v. Once again, we have a cool symmetry going on here. We start with u, everything that's left is dv by default. Then we take a derivative to get du. We take an integral to find v. Now that we have all these ingredients, we can use the ultraviolet voodoo formula. Here's the formula. The integral of u dv equals uv minus the integral of v du. So let's make these substitutions. U is x. So we have x times v, which is e to the x, minus the integral of v, again e to the x, times du. du is simply dx. So we've taken our original integral, and we've written it as a function minus an integral. This is an important concept in integration techniques. The integration techniques take a more complicated integral, such as x times e to the x, and they break it down into a simpler expression. Now that we've got this expression for the integral, we can solve this final integral. We have x e to the x minus the integral of e to the x. That's simply e to the x plus c. There is our answer. Let's double check that this answer is correct. We can always check our answers for indefinite integral problems by taking the derivative. Let's do that here. If I take the derivative of x e to the x minus e to the x, I need to use a product rule for the first term, x times e to the x. Product rule says take the derivative of the first function, derivative of x is 1, times the second, plus x times the derivative of e to the x e to the x. This expression right here is just the derivative of x times e to the x. We still need to take the derivative of e to the x. Well, derivative of e to the x is simply e to the x. And now I have e to the x minus e to the x. Those cancel. And I'm left simply with x e to the x. This is what I started with in the original integral, so I know that my solution is correct. Let's try another example. Take a look at example 2, the integral of x times natural log of x from 1 to e. We are going to solve this using integration by parts. Once again, we're thinking of an integral in the form the integral of u dv. We will choose part of this expression to be u, and everything left by default will be dv. Soon we'll talk about strategies for choosing u and how to know what to choose. But for this one, we are going to choose u equals natural log of x. We choose u equals natural log of x. By default, everything remaining is dv. So dv equals x times dx. Remember, dv will always have a dx expression in it. All right, once we've chosen u and dv, we now integrate the u function. The derivative of natural log of x is 1 over x. So we have 1 over x dx. And we integrate the v function. The integral of x dx is x squared divided by 2. Once we have these ingredients, we're ready to use the integration by parts formula. Once again, that formula is uv minus the integral of v du. So our integral becomes u natural log of x times v, which is x squared divided by 2, minus the integral of v, x squared divided by 2, times du. Du is 1 over x dx. Now, we are dealing with a definite integral here from 1 to e, and we'll use these limits once we've fully evaluated all of the integral here. All right, we still need to evaluate this second integral. We can cancel a power of x in the numerator with this 1 over x. So we obtain natural log of x times x squared divided by 2 minus the integral from 1 to e of x divided by 2. The fraction here we can think of as simply multiplying by 1/2. So to finish this integral, we have the natural log of x times x squared divided by 2 minus x squared divided by 2 over 2. This is x squared over 4. We're integrating from 1 to e, so we will use the fundamental theorem of calculus, part 2, to evaluate this expression. First, plug in e. Natural log of e times e squared divided by 2 minus e squared divided by 4 minus, now we want to use parentheses here. Now plug in 1. Natural log of 1 times 1 squared over 2 minus 1 squared over 4. There is our final answer.